We are now with this DC electromagnet, radiomagnet model, and only the radiomagnets are turned on. Next we'll turn on the DC electromagnet. Flip the polarity, turns off. Flip it so it agrees with the radiomagnets, turns on. Today we will study a new hybrid model for the DC ion drive. First we have an axial electromagnet made of 0.7 millimeter wire through which a lot of DC or AC power can pass. And then around that we've taped 6 big bar magnets made of neodymium, and they provide radiomagnetic fields which all go inward as opposed to the field of the axial electromagnet which goes lengthwise. Thus we get both axial and radiomagnetic fields from the same device depending on if the electromagnet is turned on. Inside you can see we have 2 tubes. One will be positive, the other negative 40 kilovolt DC, and in the space between those tubes will pass argon gas from this cylinder. So that's the general design. We want to see if these 2 sets of magnets together make a more powerful ion drive than either set alone. Let's see what happens now and do some experiments. Now with the DC electromagnet turned off, you can see 31 volts, no amps. The radiomagnets make the ionized argon gas spin, but only fitfully. Next, when we add power to the electromagnet, we see a big increase in both spin and ejection. Now we have both axial and radiomagnetic fields off, on. If we flip the polarity of the DC electromagnet, we lose everything because now the fields don't add together. Flip it back and it takes off. Here we have a DC electromagnet with some 6 permanent radiomagnets of a bar type around the outside. The bar magnets alone make it spin, but not too strongly. When we turn on the electromagnet as well, we get a big step up of power. Turn it off, turn it on. Flip the polarity of the DC electromagnet so it doesn't agree with the radiomagnets. We get nothing. Flip it back, tremendous power. So this hybrid model of a DC electromagnet and permanent radiomagnets of bar shape might be one way to make a new and more powerful ion drive. To conclude this video, I'm going to explain the physics in terms so simple that even a high school student can understand. When we consider ion plasma railguns, there are 2 types, linear and circular. Let's look at the linear first. I posted a video on them a few months ago. We have a north-south magnetic field and 2 long strips of conductive material such as copper. One strip gets very high positive voltage, the other negative, say plus or minus 40 kilovolt DC. When we pass argon gas between them, the argon ions and electrons get separated, and then the magnetic field converts that current into a lengthwise force down the length of the tube. This is called a Lorentz force if you study physics. It's used in all electric motors. Now, we can also have circular. Again, we have a north-south magnetic field. It's exactly the same thing. 2 pieces of conductive material, plus on the outside, minus on the inside. But instead of going down the length of the tube, they just go around in a circle, like for a donut. They don't go in or out like to produce any thrust. So now we have to go a little further. There are two general kinds of magnetic field. I'm going to call them axial and radial. The axial field is what we used in the linear railgun or the circular railgun, just an NS field perpendicular to the disk. We have charges outside and inside, a big voltage gradient. The argon gas spins around rapidly in a circle. This is not useful, however, to produce any thrust like in a rocket because it just spins and doesn't shoot out. For that purpose, we need a radial magnetic field. So, for example, we might put 3 magnets north-south all pointing inward around the disk. Now, as the ions spin around, they'll get a new curving force from those radial magnets that shoots them up and outward. Up and out, and that produces a rocket-like kind of thrust. So in this new model for the DC ion drive, we're having both axial and radial magnets. One to make them spin, the other to make them shoot out. And that was the new hybrid model we produced today, which no one else on Earth seems to have done before. But you know, as I said, even a high school kid can understand. Please put your mind to this, and let's go further forward and upward. Now when we place those 2 ring magnets with their north-facing magnetic axial field just inside the end of a somewhat larger Corbino disk, you can see again both spin motion and ejection. If we move the magnetic field away, we sort of lose the effect. Just a little spin, not much else. When we move the 2 magnets close to the end again, we again see fast spin and some ejection of gas. When those 2 magnets are right at the end of the Corbino disk, we see very fast spin, but not much ejection. We can see some ejection again when the magnets go a little past the end of the Corbino disk. We turn those ring magnets the other way so that the south pole is pointing axially. We still see very fast spin and some ejection. When the end of the disk is right in the center of the ring magnet, we just see very, very fast spin, not much ejection. And then a little past the end, it ejects quite strongly. This is a little further out. Again, it's spinning and ejecting quite strongly. Looks like a rocket, doesn't it? Next, instead of 2 big ring magnets, we're going to look at 6 bar magnets arranged radially in a circle, so all the poles point in. Again, we see a nice spin phenomenon because we have fields pointing in, and also we have a net north pole field going that way. If we move the magnets back somewhat, it doesn't spin as fast. When we move the magnets forward, it spins faster. The optimal alignment of that Corbino disk with these radial bar magnets is about 2/3 of the way along the tube. That's when it spins and ejects most, as a combination of both axial and radial magnetic fields. You can hear the propeller-like noise. Here we can see where 2 neodymium ring magnets are creating a small argon gas ion drive, 40 kilovolt DC, due to a combination of axial and radial magnetic fields. Pretty impressive, isn't it? Could we use this drive to fly through space? This is an ion drive where we have 6 bar magnets creating radial magnetic fields that point inward everywhere, and also an axial magnetic field which points north. You can see we're getting strong spin and ejection of argon gas when it's ionized. Could this be a space drive? Very possibly so. The flow rate of argon gas through this device is very slow. You can just hear a little hissing. So almost all of the acceleration we're seeing is due to electrical magnetic fields.